So we have just seen that a periodic signal can be decomposed in a sum of sines, cosines at the fundamental frequency and the harmonics. So this is a frequency representation of the signal, and it is a great tool for signal processing. Of course, it would be nice to have that kind of frequency representation not only for periodic signals but for aperiodic signals. So what we'll do is kind of see this aperiodic signal f of t as a periodic signal with a period that is tending to infinity. And mathematically you can write it like this. Okay, so if we start from the Fourier series and we use this trick, we'll end up with the Fourier transform, and the Fourier transform will be tackled in this second video of section 5, Fourier frequency analysis. The idea here is to write the following. F of t is the limit of a periodic function, so this function is periodic, and we'll let the period tend to infinity. Okay, so f of t is aperiodic, and we write it as the limit when the period tends to infinity of a periodic function. So if f tilde is periodic, we've seen in the previous video that you can write the Fourier series representation. Omega 0, that's the fundamental, and here you can compute also the Fourier coefficients. Okay, so this is nothing new, and what we'll define is this f over here, and this will be the future Fourier transform, and it is t times the Fourier coefficient to get rid of the 1 over t over here. Omega k will be, well, these all the frequencies, right, the harmonics, and delta omega is the fundamental frequency. It's 2 pi over t, and what we can do now is plug all these quantities in the two equations above, and we've got here f tilde, right, ck, this is ck, this comes from this equation over here, and 1 over t, this is 1 over t, comes from this equation over here, right? And what we have done is replace k omega 0 with omega k. We've done it here, 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 and here, right? T times ck, that's my f, is this integral that you've got over here. Just we got rid of the 1 over t, and k omega 0 has become omega k. So we see that when t tends to infinity, f tilde tends to t, but we see also that delta omega will be becoming infinitely small. Okay, so we'll have something that becomes infinitesimal, so delta omega becomes d omega, and well, here these quantities, these harmonics of the fundamental, they will become closer and closer until you get a continuum. Okay, so you obtain a continuous variable. Omega k tends to omega, right? And the sum over here will become an integral. So we end up with, so this was f tilde. If you look at this equation over here, we obtain in the limit when t tends to infinity, 1 over pi, we can get it out of the integral, minus infinity of f omega exponential of j omega t, and here it's d omega, right, because we still have the time dependence, and here f omega, the Fourier transform, is the limit from minus infinity to infinity of f of t exponential of minus j omega t dt. So this is the Fourier transform, and this is the inverse Fourier transform. So these are the two formula that we have, well, kind of found in the previous slide using this limiting argument. And remember that the Fourier transform is obtained from the Fourier series using this idea of taking a function that is periodic and letting the period tend to infinity and see what happens. Okay, so we obtain then a transform that is valid also for aperiodic signals. You can see also when you're looking at the inverse Fourier transform that f of t is decomposed in a sum. Well, now there is a dependence on all frequencies, so this sum comes in the form of an integral, but it's a sum of complex exponentials. Okay, and each complex exponential or each frequency comes with a certain weight, f of omega, and f of omega is indeed the Fourier transform of the signal f of t. So the idea is exactly the same as with the Fourier series. Of course, there are conditions for the existence of the Fourier transform, and since we have used the Fourier series to kind of find the Fourier transform, well, it's kind of obvious that the conditions are the same, so they are the Dirichlet conditions, right? And there is one main condition, that the function f of t must be absolutely integrable. So now that's on the interval minus infinity infinity, so this means that this integral here of the absolute value of f of t must be bounded. There are also these, well, more technical conditions on the number of maxima and the number of discontinuities that needs to be finite, but in practical examples this is always the case. So remember that the inverse Fourier transform is 1 over 2 pi integral of minus infinity to infinity of f of omega exponential of g omega t d omega. You know, of course, that omega is 2 times pi the frequency, so you can also decide to work with a variable that is f over here. Okay, so if you do that, d omega will be 2 pi df. Okay, and the nice thing about it is that this 1 over 2 pi will be disappearing. Okay, so this is the Fourier transform if you decide to work with the variable frequency, and this is its inverse Fourier transform. And you'll see this sometimes in the literature. We have stick to the other definition because it's closer to the definition of the Laplace transform, as we will see. So let us take an example of a Fourier transform of this signal over here. So this is a rectangular impulse that we have defined in section 2, and we have used the scaling property to give it a width of t. So what we can do now is compute the Fourier transform, and here we have the definition. But since, well, the function f of t is 0 outside the interval minus t over 2 t over 2, we can simply bring this back to an integral from minus t over 2 to t over 2, and f of t in this interval takes the value 1, so we have the 1 over here. So if we integrate this one, we obtain the same function of time, and we have to divide by minus j omega at the limits, integration limits, minus t over 2 t over 2. So this is what you obtain. By now you should recognize that this is, well, a sine but multiplied by 2j, right? And this one and this one will cancel out, and the minus and the minus will cancel out. So this is what you obtained. Of course, omega, it's 2 pi over the period, and you can inject that in here, and here we put t over here and 1 in the denominator, so they could cancel out, but you leave it as it is on the screen because you kind of rewrite this by using this equation over here, and this is the definition of a cardinal sine. Okay, a cardinal sine is the sine of pi t divided by pi t, and if you write it like this, you see that the Fourier transform of a rectangular impulse of duration t is a cardinal sine. Remember also that the limit when t tends to 0 of this sine pi t over pi t, and so this cardinal sine, it's written sinc, is equal to 1. This Fourier transform of the rectangular impulse will be used extensively in the next section on sampling theory. We can make two other remarks about this Fourier transform. The first one is that because of this property of the cardinal sine, when the argument tends to 0, we see that the contribution at the 0 frequency in the Fourier transform will be simply t. What we have here also, second remark, is that this Fourier transform of the rectangular impulse is a real function, okay, because the sinc function is a real valued function. So what we see here is the frequency representation of this rectangular impulse. Remember that the Fourier transform decomposes the signal in a sum of complex exponentials, and the Fourier transform gives the contribution at all frequencies. The sinc function is shown on the screen for t equals 2 here, and you can see that it has infinite support, so there will be contributions at all frequencies, even if at high frequencies, of course, the contributions will become smaller and smaller. So here we have decided to show this Fourier transform as a real value, okay, that can be positive and negative. The alternative could have been to show the absolute value and then to add a phase spectrum where the values are positive, you would have a 0 phase, and where it's negative, the phase would be minus pi or minus 180 degrees. Notice that there are no contributions at multiples of 1 over t, and at the frequency f is equal to 0, the contribution is t. So if you decrease t, well, obviously this contribution will decrease, and if you increase t, this contribution will increase. Remember also that if you look at this rectangular impulse and you let t tend to infinity, well, you'll have a higher and higher contribution at the 0 frequency. This is kind of obvious because when you let t tend to infinity, you'll have a constant signal and you'll have only contributions at the 0 frequency. This is what we'll see later in the course when we compute the Fourier transform of a constant signal. Well, you probably have noticed the similarity between the Fourier transform and the Laplace transform. Remember that the Laplace transform of f of t is, well, the integral from minus infinity to infinity of f of t e to the minus st dt, right? And remember that s is equal to sigma plus j omega, and that's, well, this Laplace transform f of s as a region of convergence. So this is the region where the Laplace transform is defined. Well, it's all s as defined here, such that the following integral f of t e to the minus sigma t in absolute value convergence. Okay, so this is the region of convergence. So you see, when looking at the Laplace transform and looking at the Fourier transform, that if you do this trick over here, well, everything is nice and easy. Okay, but remember that S is sigma plus j omega. When you write this, you kind of ask that this Laplace transform is defined when sigma is equal to 0. So you can do this trick only if the region of convergence contains sigma is equal to 0. Okay, so if and only if sigma is equal to 0 is in the region of convergence of f of s. Okay, if sigma is equal to 0 is in the domain of convergence, this means that this integral here, but with sigma is equal to 0, convergence. So this means that the function is absolutely integrable and that the Dirichlet conditions are met, and that you can indeed speak of a Fourier transform that can be computed using the usual formula. Okay, so do not generalize this property over here if the region of convergence does not contain sigma is equal to 0. Sigma is equal to 0, remember, is the imaginary axis. There are a few Laplace transforms that you know and that we use quite often. The step signal, for instance, and the Laplace transform of sinusoidal signals that have Laplace transforms with regions of convergence that do not contain the imaginary axis. Okay, remember that the Laplace transform of u of t is 1 over s, but the region of convergence is sigma positive, and sigma is equal to 0 is not in the region of convergence. So you cannot simply take f of s and replace s by j omega, right? But as we will see in the next slide, well, there are cases where this trick is very handy. For instance, if the function f of t has finite support, because if the function f of t has finite support, its Laplace transform will have a region of convergence that is the whole s-plane. Okay, so obviously sigma is equal to 0 will be in this region of convergence. In general, the Laplace transform will be used for situations where the transient and the steady state behavior is important, and the Fourier transform will be used if only the steady state behavior is important. Well, in general, what you'll do is use the Fourier transform to kind of analyze the frequency content of a signal. As a conclusion, you can obtain the Fourier transform of a signal f of t from its Laplace transform if the Laplace transform has a domain of convergence that contains sigma is equal to 0. If this is the case, you take the Laplace transform and you replace s by j omega. The fact that sigma is equal to 0 is in the domain of convergence of f of s simply says that the function f of t is absolutely integrable. So let us apply this to this rectangular impulse, and the first question is, can we obtain the Laplace transform from the Fourier transform? So the condition was that the region of convergence of f of s, the Laplace transform of f of t, must include the j omega axis, sigma is equal to 0. Well, first of all, remember that functions that have a finite support, and this is clearly the case for our rectangular impulse, have Laplace transforms with a region of convergence that is the whole S-plane. So obviously the j omega axis, sigma is equal to 0, is going to be part of the region of convergence. So yes, we can do this. Let us then first compute the Laplace transform of our rectangular window. So we can construct the function f of t using two steps, right? One that is in minus t over 2 and another one in t over 2. We know that the Laplace transform of a unit step is 1 over s, and now we have to use the time shifting property. If we use the time shifting property, well, we'll have exponentials appearing in the Laplace transform. Okay, so now what we can do is simply replace s by j omega, and very quickly we obtain what we have obtained previously using the Fourier transform. Okay, and indeed we obtain, without a surprise, the same result. So in this slide we talk about the frequency shifting property of the Fourier transform, and it's kind of obvious that the Fourier transform has this property. Remember that it is also a property of the Laplace transform. So here, if you know the Fourier transform of the function f of t, and it's f of omega, you can then also obtain the Fourier transform of the following time signal. Well, this function f of t multiplied by complex exponential will have a Fourier transform that is the same as the original one, that is frequency shifted by omega 0. This can be shown very easily. So this is the Fourier transform you're looking for. So if you take the definition, this is what you obtain, and using the properties of the exponential, you obtain this integral over here, and this is simply the Fourier transform of the original signal f of omega that has been shifted in frequency by omega 0. Remember, we had this very same property for the Laplace transform. A few words about this notation. So this means that, well, the Fourier transform will lead you in this direction, and it will take this time signal and produce this Fourier transform. And if you go from the frequency domain to the time domain, well, it involves, of course, the inverse Fourier transform. And very often in this section we'll talk about Fourier pairs. Okay, it will be a function of time with the associated Fourier transform. We can use this frequency shifting property of the Fourier transform to compute the Fourier transform of an amplitude modulated signal. So the original signal is f of t, and it has Fourier transform f of omega. So amplitude modulation consists in multiplying f of t by a sinusoidal type signal, and in this case it will be a cosine. Okay, so this is the amplitude modulated signal, and this cosine is called the carrier, and the frequency of this carrier, the carrier frequency omega 0, is typically higher than the maximum frequency of the incoming signal. Okay, so this modulated signal, okay, the original signal f of t times the carrier, can be rewritten differently using the Euler identity. Okay, and we have seen, for instance, that the Fourier transform of this one is f of omega minus omega 0. So you take the original Fourier transform and you do frequency shifting. So we see that the Fourier transform of this amplitude modulated signal is given here, and we see that the transform of the modulated signal is the original spectrum of Fourier shifted to the frequencies omega 0 and minus omega 0, and of course you have here this multiplication by 0.5. Here is an application of this property using the Fourier transform of an amplitude modulated signal. So the original signal here is given at the top left. It's in triangular impulse, and if you compute its Fourier transform, and the MATLAB code is given later on in the slides, this is what you obtain, right? And you see here that, well, the energy is at low frequencies, and at, well, frequencies that are higher than, let's say, 6 radians per second, there is almost nothing. Okay, so here we multiply this triangular impulse by a carrier, which is the cosine of 10t, and here you see that the carrier frequency 10 radians per second is at frequencies where in the original signal or the original spectrum you see little or no contributions. Okay, so this is how it looks like, and indeed you recognize here the envelope of the original signal. If we now compute the Fourier transform of this signal, you see indeed that this original spectrum has been shifted to minus the carrier frequency and that the amplitude has indeed been multiplied by 0.5. So you have 2.5 here and you have 5 over here. The applications of amplitude modulation are first telecommunication. As you know, acoustic signals are audible up to 20 kilohertz, and if you want to emit these signals through the airwaves, well, you need an antenna, and the length of that antenna is actually related to the wavelength divided by 4. As you know, the wavelength is the speed, in this case the speed of light divided by frequency. So if you want to emit a signal with a frequency content up to 30 kilohertz, and this is to make the calculations easy, you see that the wavelength is 10 kilometers and the length of the antenna would be 2.5 kilometers. Okay, so this is impossible. But if you do amplitude modulation, you can see that, as we've seen in the previous slide, well, the frequencies are shifted to much higher frequencies, and it becomes then possible to transmit the signal over the airwaves. Some faults, mechanical faults, gearboxes, bearings is a roulement in French, well, they introduced amplitude modulation. Developing bearing faults, for instance, produce periodic impacts, and these periodic impacts, well, they depend on the bearing geometry, and these impacts excite structural resonances, and this results in amplitude modulation. So the signals are picked up using a vibration measurement, okay, and you have to then to do amplitude demodulation before you can see the fault appearing in a spectrum. This is what I've shown you at the beginning of the course. Remember the formula of the, well, Fourier transform. So the Fourier transform f of omega is the integral from minus infinity to infinity of f of t in the exponential of minus j omega t dt, and the inverse transform that produces f of t is 1 over 2 pi integral from minus infinity to infinity of f of omega e.g. omega t d omega. And when you look at these two formulas, well, you can see that there is some similarity, okay? The differences are over here, of course, and here it's a minus, there a plus, and here you integrate with time and there with omega. But you can see already intuitively that if you take 2 pi, this is to get rid of this one, and you take this function here and you make it a function of minus omega, well, this will be the Fourier transform, okay, of the function that is over here, but that is now considered as a time function. This will be proved formally in the next slide. So this is how we arrive at time frequency duality. And time frequency duality says that if you have a Fourier transform pair, and here it is, f of t, and here is its Fourier transform, then you can construct a so-called dual Fourier transform pair by considering this one as a time function, and the Fourier transform of this function over here will be this one considered as a frequency function that is reversed times 2p. Right, so from one Fourier transform pair you can construct the dual one. So this property will allow you to obtain new Fourier transform pairs from known Fourier transform pairs, and this is, well, kind of neat, for instance, for Fourier transform for which it's difficult to use the formula, or for which it's difficult to use the Laplace transform and replace S by j omega, because sigma 0 is not in the domain of convergence. And we'll use this time frequency duality, for instance, to compute the Fourier transform of a sinusoidal signal. So here's how you go from intuition to something that you can prove formally. So this is the formula of the inverse Laplace transform, and here you integrate with respect to omega, so this is why this variable disappears over here. Here we call this variable omega, but we might call it anything else because it disappears during integration. So what we do over here is write the same formula, but instead of calling this variable omega, we call it a rho, just to allow you to swap this variable over here and call it now minus omega. Okay, so we take this formula over here and now we replace t by minus omega. This is what you obtain. Okay, and now we integrate with respect to rho, and this is, well, kind of disappearing from the integral. Okay, when you integrate, and it only depends on omega, so this rho you might call it something else. Well, here it's more interesting to call it t, because then you find the definition of a, well, Fourier transform. Okay, so we have that this thing over here is equal to this integral, and this is indeed the Fourier transform of f of t, right? So if we have a first Fourier pair ft f of omega, then we can construct another one. We consider this one as a time function right now, and then its Fourier transform will be simply this one that you consider as a frequency function with reversal, so f of minus omega, and you multiply by 2 pi. Okay, so as said previously, from one Fourier pair you can construct another one. So here we compute the Fourier transform of a delta. Okay, and the idea here is that you can use the Laplace transform. The Laplace transform of a delta is 1. Okay, and the region of convergence is equal to the S-plane. Okay, so sigma is equal to 0 is, of course, in the region of convergence. So what we can do is simply take the Laplace transform 1, okay, and evaluate it in S is equal to j omega. So this is 1. So here we have shown that the Fourier transform of a delta is 1. So the Fourier transform by linearity of A times delta is, of course, A. So this is our first Fourier pair. And now what we can do, okay, so this is f of t, and this is f of omega. What we'll do, we'll consider this one as a time function. So this plays the role of capital F t. And then what we have to do is to take this one, consider it as a function of omega, do time reversal. This is f of minus omega, and we multiply by 2 pi. But the delta is an even function, so you can replace this by this relation over here. Okay, so this is the Fourier transform of a constant is 2 pi delta omega, and here we need the amplitude, of course. So what is the interpretation of these two Fourier transforms? The Fourier transform of an impulse is 1. Okay, so this means that, well, the frequency content is 1 over all frequencies. So a delta contains all frequencies, so in practice it will be impossible to create, right? And another thing that you can see is that a constant signal only contains, well, energy at the 0 frequency, which is kind of obvious, and this is something that we already had observed at the beginning of this section on the Fourier transform, when we had considered the Fourier transform of a rectangular impulse. Remember that when the width of the impulse was growing, we could indeed see that the energy content at the 0 frequency was growing as well. So in the preceding slide we had used time frequency duality to find the Fourier transform of a constant. Now we'll use this same property to find the Fourier transform of a cardinal sine. Remember that at the beginning of this video, at the beginning of this subsection on the Fourier transform, we had found the Fourier transform of a rectangular window, right? And we had seen that it was a cardinal sine and that it could be written like this. Okay, so this will play the role of f of t, and here we have its Fourier transform f of omega. So to use time frequency duality, we'll consider this one as a time function, okay, and we'll simply also replace t over 2 by omega 0. So if you take this one and you make it a time function and you replace t over 2 by omega 0, you have this quantity over here, and so we can rewrite it as f of t. And we had seen that using time frequency duality, well, you have to take this function here, consider it as a function of frequency, do reversal, and then multiply by 2 pi. If you do this, this is what you obtain. But again, this, well, rectangular window is an even function, so you can also rewrite it like this. Okay, so what have we obtained? Another way to write this, we can kind of cancel out this one over here and this one, and we can divide by pi, and we have that the Fourier transform of this signal here is a rectangular window but in frequency. Okay, so time frequency duality says that, well, the Fourier transform of a rectangular window in time is a cardinal sine, okay, and the Fourier transform of a cardinal sine is a rectangular window but in frequency. This is something that will be used extensively again in the next section on sampling theory. So we have seen previously that the Fourier transform of a delta is equal to 1, okay, and what we do here is the sum of two deltas, one that is localized in minus tau and the other one at tau, and we know that if we shift in the time domain, what will happen is that you multiply by e.g. omega and tau over here and minus tau over here. This is the frequency shifting property of the Fourier transform. So what you recognize over here, if you take the Fourier transform of two pulses, one in minus tau and one in tau, is that you obtain, and this is by the Euler identity, 2 cos of omega tau. Okay, so this is now playing the role of f of t. This is one Fourier pair and its transform is over here, and you kind of see what we'll do. We are interested in the Fourier transform of a cosine, so what we'll do is use time frequency duality, right? So we'll consider this one as a time function. Okay, so this is what we've got over here. This is f of t, right? And we know that the corresponding Fourier transform will be this one, where t is replaced by minus omega and where we multiply it by 2 pi. So if you do this, this is what you obtain, right? And this is, you can go from this expression to this expression because of course the delta is an even function. Okay, so replacing tau by omega, we've got here the Fourier transform of a cosine. And of course the cosine only contains one frequency, so you see that you have indeed here information only at omega is equal to omega 0 and omega is minus omega 0. Okay, so we had to use this trick of time frequency duality because the initial function, this one, is not absolutely integrable, so it's not possible to use the definition, the standard definition of the Fourier transform, and it's also not possible to use this trick with the Laplace transform because sigma is equal to 0 is not in the region of convergence of the Laplace transform of a cosine. The Fourier transform of a cosine, as we have just seen, is given by this expression over here. So it's two Dirac impulses, one located at omega 0 and the other one at minus omega 0. So if we decide to work with a Fourier transform that works with the variable f, as we have defined at the beginning of this video course and the beginning of this section on the Fourier transform, you can obtain this relation over here. And what you see here is that the Fourier transform of a cosine at frequency f0, it's the sum of two deltas of amplitude a half, one located at f0 and another one located at minus f0 over here. In here everything is real, so we just show the amplitude spectrum. I could show the phase spectrum, but of course there everything would be equal to 0, even at the frequencies f0 and minus f0. This should not come as a surprise. If it does, you should go back to section 2, where we have seen that a cosine can be constructed as the sum of two phases, one exponential of jf0t plus another exponential minus jf0t, right? So the half you see here at the amplitude a half, and we see that in this cosine there are two frequencies, indeed one at f0 that's rotating, and it's a phasor rotating counterclockwise, and then at minus f0 that's a phasor rotating clockwise, right? So this you can see very clearly in the second animation that shows that a cosine can be obtained by the vector sum of two phasors and then multiplying by a half. So now we can obtain the Fourier transform of a sine only with a few changes. Okay, it's the same slide as before, but we have a minus sign over here. Remember that a delta has Fourier transform 1, so if you shift it, it will be 1 multiplied by an exponential. This is what you've got over here, and the reason why we take a minus is that we this time you obtain a sine. Okay, so this is the Euler identity. Again, this is f of t, it's Fourier transform f of omega, so we'll consider this one as a function of time. So this is f of t, uppercase f of t, and we know that the Fourier transform will be by time frequency duality 2 pi times the function of time here, but with t replaced by minus omega. This is what you obtain. Again, the delta is even, so you can rewrite it like this. We can divide over here, put the pi here at, no, we'll leave it there. The opposite, the j goes below here, and we have now the Fourier transform of a sine. It looks a lot like the previous formula, and from a modulus point of view it will be the same. So there will be energy at omega 0 and minus omega 0, and there will only be a difference as far as the phase is concerned, and we'll see this. So again, why do we do this trick? It's because the Fourier transform cannot be obtained using the integral definition. This function is not absolutely integrable, and we cannot use this trick with the Laplace transform, because the Laplace transform of a sine has a region of convergence which is sigma larger than 0, and the j omega axis is therefore not included in the region of convergence. We have just seen that the Fourier transform of a sine is given by this expression here, and again what we'll do, instead of working with omega in radians per second, we'll work with f, the frequency expressed in hertz, and this is then the result that you obtain. And again, this should not be a surprise, because using Euler's identity you can rewrite this sine as 1/2 an exponential at jf0t minus exponential of minus jf0t, and here there is a j lacking at the denominator. Okay, so indeed this is what you see over here. So if you take the modulus, the amplitude spectrum, you see the half over here, and you see indeed energy at f0. This is coming from this phasor that is rotating counterclockwise, and energy at minus f0, this is coming from this phasor that is rotating clockwise. Okay, and the only difference with a cosine lies in the phase. Indeed, what you see here in the phase spectrum is that this phasor is lagging by 90 degrees, okay, and this phasor here is leading by 90 degrees if you compare it to the cosine. So it is also possible to compute the Fourier transform of a periodic signal. Well, a periodic signal, it's periodic, and we've seen at the beginning that these type of signals are not absolutely integrable, okay? So we cannot use the formula of the Fourier transform to obtain something, so we kind of need to circumvent this problem, and the way we do this is by using the Fourier series decomposition. If the signal is periodic of period t, we can write f of t using its Fourier series representation, and what you've got here is a constant, right? And we know that the Laplace, not the Laplace, the Fourier transform of a constant is a delta, but since we multiply in the time domain with an exponential function, what this will do is actually do frequency shifting in the frequency domain. Okay, this is the frequency shifting property that we've used before. The Fourier transform of a constant was 2 pi a delta omega. So if we use this property with the frequency shifting property, okay, this is what we obtain. Okay, and we see that the spectrum is indeed discrete, and that we'll see, well, contributions at omega 0, minus omega 0, and the multiples of these frequencies, so the harmonics. Well, just for your information, this is not something I'm going to ask you at the exam. Remember that this is the energy, but the energy, well, kind of computed in the time domain. Well, if you go to the frequency domain using the Fourier transform, you can kind of see that the energy is preserved, okay, and this is called Parseval's energy conservation law. Well, this concludes this second video on Fourier frequency analysis.